The next question I'd like to look at with you on the Intermolecular Forces free response question assignment. It comes from 2003. Again, as with the last question, I don't want to look at every part of the 2003 free response question. We'll just pick out a couple of parts maybe that have some things involved that we haven't already gone through together on previous parts. You should certainly work on the others as well. At this point, we haven't, at least in this year, we haven't looked at chemical reaction equations all that closely. And so predicting chemical reaction equations might be less familiar for many of you at this point. So if you haven't already gotten to this question or just getting into it now, I might say hold off on letter A because that involves a chemical reaction equation that you might not be familiar with at this point yet, and that we'll get to more as we get into chemical reactions. And as it hints at there, as we get into acid chemistry, we'll talk more about that sort of stuff too. So for now, we're going to look at B, part 1, and letter C on the 2003 free response question. So on B1, it mentions that table salt and sugar, when they're dissolved into water, they increase the boiling point over pure water. In other words, pure water, hopefully you know, boils at 100 degrees Celsius, and then when we add salt or sugar to water, it'll boil at a higher temperature. So this question is sort of asking why. In terms of intermolecular forces and chemical principles of those things, what's causing the boiling point change when salt and sugar are added? That's basically what it's getting at. So to kind of get to that, I want you to think about with these, pardon me, let me switch pens. I want you to be thinking about, as ask questions like this, since we're talking about the property of boiling point, be thinking, what determines the boiling point of a liquid like water? What determines boiling point? And you don't need to write all this out, but you want to think about it. What determines the boiling point of water? Well, boiling, as you know, is going from liquid to gas phase. So the boiling point is the temperature at which there's apparently something to do with enough energy for that liquid to be converted to a gas. Now, it has to do with the atmospheric pressure and an equilibrium between the vapor pressure of the water at that temperature and the atmospheric pressure as well. But we're going to get to that more when we get into gas behaviors. At this point, we want to know that boiling point is a function of how attracted the molecules are to each other in the liquid state. So boiling point is a function of intermolecular forces. In other words, as intermolecular forces are going up, it'll require more energy to boil a liquid than it did before. So more intermolecular forces or stronger intermolecular forces means a higher boiling point. That's really, really simple. Boiling it down to the simplest of little bullets, increasing intermolecular forces means increasing boiling point, generally speaking. Now, that's quite simplified, but for the purposes of this question, it works because we're talking about water boiling all throughout part B. And so why does water have a different boiling point than sugar water or salty water? And it has something to do with those intermolecular forces. And apparently, if the boiling point's going up with salt or sugar added, higher boiling points, as the question suggests here, that must mean that salt water and sugar water have more or stronger new types of intermolecular forces compared to just plain pure water. So let's look at it. Well, what intermolecular forces are present in plain water? Well, hopefully we know that H2O, as we look at that molecule, H2O has a rather strong dipole as we draw its Lewis structure. And we've already identified this a number of times, but we know that water has a pretty strong dipole in this direction. And so we typically label the oxygen end of the water molecule as slightly negative, and hydrogen's end as slightly positive. Either the two hydrogens or just the region between the hydrogens as slightly positive. So water is a polar molecule, so it has a dipole. And not only that, it has the kind of dipole that allows for hydrogen bonding. And hydrogen bonding is usually considered a little stronger type of dipole-dipole bonding. So water contains hydrogen bonding. And so for water to boil at 100 degrees Celsius, it has to overcome that hydrogen bonding that's present. So the boiling point of pure water, 100 degrees Celsius. Now, why would adding sugar or salt cause an increase in boiling point, which we believe is an increase in the intermolecular forces present in the water? Well, there's the thing. When we add sugar to water or when we add salt to water, we're putting solute particles into the water as well. So water plus a solute like sugar will have not only all the things that water has, which is hydrogen bonding, it'll have hydrogen bonding as well, because water has it and it's still got water in it. Plus, it's going to have additionally attractions between the water and the sugar. Okay. Water-sugar interactions, water-sugar intermolecular forces. Now, what are those? Well, water we know is polar, and sugar has a great big large structure within which there are a number of OH tails. kind of on it, or oxygens bonded to carbons at least. And so when we look at a sugar molecule, there are polar regions within the sugar molecule too. So water's polar, sugar's polar, and so we have between water and sugar dipole forces as well, and those are attractions. Those are additional attractions on top of what plain water already has. Okay, so water has additional attractions when it has something dissolved into it. The plain water's hydrogen bonding, as before, the same hydrogen bonding we had over there is back again, but now we have additional dipole forces that have been added in when it comes to adding sugar into water. So, in other words, water has lesser or fewer or weaker total intermolecular forces. The sum of the intermolecular forces in water is less than the sum of the intermolecular forces in water plus sugar. That's kind of what we're getting at. I won't write out a sentence for it. I'm going to let you phrase that yourself, but that's kind of the idea when it comes to why. Now, what about water and salt? Water and salt, when we dissolve salt into water, we get sodium chloride, an ionic salt, dissolved, and that splits into sodium ions when it dissolves and chloride ions. And so we have ion and ions surrounded by water. How does that look? Well, I think we've looked at it before, but I'll draw it in here one more time. Basically, sodium ions, positive, are going to be interacting with a water molecule, which has a slightly negative end on the oxygen side. We know we label this as slightly negative, slightly positive down here, slightly positive down here. And so we're going to have this intermolecular attraction going on, which is truly known here as an ion dipole attraction. An ion dipole force or ion dipole attraction. That's pretty significant. Now think about a dipole, like we noticed, like we mentioned over here. Think about a dipole in sugar with water. A dipole is not as strong. It's a partial charge, so it's not as strong as a true ion charge, where it's a true +1 or a true -1 or a true +2, whatever that ion might be. So an ion dipole attraction, we could probably look at this and say, this is typically going to be stronger than a dipole force. This is stronger than even what we'd find in sugar water. And so when we have ion dipole attractions, those are going to be substantial. Ion dipole is greater than dipole, especially when we're talking about water in both cases there. So sugar is going to increase the attractions that plain old water would have by adding more of its own attractions. But ion dipole attractions are even more substantial than that. And if we want to show too how chloride would interact with water, well, chloride being negative here, -1, pardon me, is going to have another ion dipole attraction. So there's another one right in there. We're talking about between chloride and water. So we have ion dipole attractions with sodium and water. We have ion dipole attractions between chloride and water, and ion dipole attractions on top of what the water already has, which is those hydrogen bonds of its own. Again, the sum of the intermolecular forces in salt water, which is hydrogen bonds plus ion dipole attractions, is going to be greater than just the hydrogen bonds that pure water would include. And so, keeping in mind, what have we glossed over in all three of these examples? Plain water, water with sugar, water with salt. I've glossed over the fact that in each of these cases, they would also, all of them, have London dispersion forces. And typically, if there are dipoles present, we're going to talk more about those. Everything's got London dispersion forces too, but in addition to that, we have what's usually a stronger consideration if there's nothing more present, then London dispersion forces matter a great deal. But when we can add on top of that dipoles, or we can add on top of that hydrogen bonding or ion dipole attractions, that's just one more thing that's present in all of them. So it's kind of a common denominator, sort of like a side item that all of them come with as well. So plain water has fewer attractions or weaker attractions, just hydrogen bonds, then water with sugar, which has hydrogen bonds plus dipole attractions between water and sugar. And then salt water would include the hydrogen bonds between the water molecules plus the even stronger ion dipole attractions between sodium and water as well. This is why syrups don't evaporate very quickly. If you have a very concentrated sugar syrup, syrup won't evaporate. You put a drop of syrup on your countertop after having pancakes or something, and that syrup droplet will stay there for days compared to if you put a drop of water next to it. The water will evaporate in hours, but the sugar, such a strong intermolecular forces in syrup, that sugar holds the water into that droplet far, far longer, and so syrup doesn't evaporate very fast. Same thing's true of salt water, by the way. If we look at things like our sidewalks in the winter, if you put down too much salt, on your sidewalk and you watch the snow melt, and then maybe the wind comes up and kind of starts to dry things off, the places where you put salt down on your driveway, where there's actually a thin layer of salt water then on top of your sidewalk or your driveway concrete, that salt water area will stay damp a lot longer than areas that you didn't salt. And the big reason is because water's there and it's being held into that liquid state, kept from evaporating, because you've added so much salt. And those ion dipole attractions in that salt water on your sidewalk keep the water in a liquid state far longer, even when it is windy and the sun starts to shine. So next winter, something to look forward to looking at. As you look at the sidewalks, you can think about chemistry in a whole new way and still watch your step. All right, let's look at letter C. Methane does not behave as an ideal gas at low temperatures and high pressures. Now, I'm going to confess, at least this year as I record this video, we haven't defined ideal gases really. We talk about them in first year chemistry briefly, and then we don't come back to them in AP chemistry, at least we didn't this year, until a little bit later in the year. So I'm just going to remind you, if you didn't Google it, which of course I think many of you probably would, what is an ideal gas? Now I'm going to keep it simple. An ideal gas is it's a hypothetical. The ideal gas would do this. In fact, no gases are truly ideal, but most of them are ideal most of the time, kind of like friends or family members. I love you most of the time, but there are times when you're not ideal and you drive me a little crazy. Well, gases, gas particles, they behave in an ideal way most of the time, but sometimes they don't. And this question gets to the heart of that. So what is an ideal gas in terms of its behavior? In an ideal gas, the particles of gas, the gas particles, experience no intermolecular forces. Zero intermolecular forces. In other words, there are no attractions between the particles. Remember, intermolecular forces are really always some kind of attraction. There's no repulsions to speak of that are anywhere nearly as important or significant as the attractions that we talk about between positives and negatives, or even in our London dispersion forces. So, as we look at gases that are behaving ideally, we would say that the gas particles in a sample, and this question is talking about methane, CH4, methane gas. Methane particles, it's claiming, shouldn't experience any attractions to each other because methane should behave as an ideal gas. But the question says at low temperatures and high pressures, methane doesn't behave in an ideal way. Why is that? Well, when do ideal gases stop behaving like ideal gases? When do gases stop behaving like ideal gases? And the idea is that most of the time, and this is all just kind of background, you wouldn't need to put all this down. So if you already have a really good grip on what an ideal gas is and how it behaves, and this is kind of all just background that you maybe don't need to hear again. But I'm going to put it in here because I know this year, as I record this, we haven't talked about ideal gases a whole lot in my class yet, and I want to give you guys that are here for that year a bit of background. Most of the time, gas particles are so far apart that they don't feel each other. So there's so much empty space in between particles that they don't feel each other's presence. So they don't feel each other's attractions. They don't experience attractions. So even if I am a slightly polar gas molecule, like say carbon monoxide or water vapor, I don't necessarily find attractions between myself and the next carbon monoxide or the next water vapor molecule, because we're so far apart and we're moving so quickly that we kind of just tap into each other and we bounce off of each other in a way that we describe as being elastic. So there's no loss of kinetic energy. It's as if they bounce off of each other and there's no interaction whatsoever. That's what an ideal gas is. When would this no longer hold up? In other words, most of the time, when's the other time? Well, that would be when gas particles aren't so far apart that they start to feel some attractions to each other. So how can we get gas particles closer to each other? Well, you can put them into a much smaller container, pack them into a tighter container, a smaller space. And if you look back to the question, it says high pressure. Well, high pressure would mean putting the particles closer together in a smaller space. So they're running into each other, and the container that they're in, they're running into those things far more often. And that's what we measure as a higher pressure. High pressure, and or another way to get gas particles to come very close to each other then is if we drop the temperature way down, because at low temps, gas particles slow down and they begin to sort of interact with each other a little bit more often, and they don't bounce off of each other so quickly. It's sort of they hit each other in slow motion almost compared to at higher temperatures, and it gives their electron clouds a chance to interact with each other's proton nuclei. And so the intermolecular attractions, or the polarity of the molecules, all of that starts to matter more when the particles are closer to each other, when they're bumping into each other more often, and they have a moment when they do tap into each other more often to sort of feel attractions to each other. And pretty soon, high temperature, low pressure, together, this means the particles are getting very close together by comparison. And when the particles are closer together, the intermolecular forces start to matter. IMFs start to add up. They start to matter more. It gives those electron clouds a greater opportunity to interact with each other. And so as those happen, this leads to what we call non-ideal behavior, because now particles aren't sort of oblivious to each other like before. Okay. Before we mentioned they're so far apart that they don't experience attraction. Well, now those intermolecular forces start to matter more because the particles are getting closer together. All right. So that's the idea with ideal gas and non-ideal gas behaviors. Typically, we'll say those are the conditions that would lead to gases behaving in a non-ideal way: high pressure and low temperature, either one or both. Especially if you can do both, then you can get particles especially close together, and you get them slowing down, which helps them to find each other. So if we want to get a gas to liquefy that doesn't typically want to liquefy, we have to put it at low temps, we have to put it at high pressure, and find ways to get those particles to find each other, and they form a liquid by attracting to each other and clumping together or sticking together, and then pretty soon they'll stay as a liquid if we can maintain those conditions for a long period of time. That's kind of the way that we keep liquid nitrogen from turning into gaseous nitrogen. We keep that liquid nitrogen in a very insulated container where the temperature is very, very low, and that makes its boiling process happen at a much slower rate. So the particles will stay as a liquid a lot longer. All right, so water, being a very polar molecule, water is one that we can easily change states. We can make it change states quite readily, and by making those particles slow down, by changing their temperature, we can make them stick to each other and clump together and form a liquid far more readily. And hint, hint, that's what kind of leads you to the ideas of question D here in 2003. But for now, I'm going to stop right there and end with our questions for 2003. Let you work on the others, and we'll pick it up on the next video with questions from 2004. We'll see you then.